introduction has been said, why physics is giving talk on chemistry. Okay. Actually, when I was doing my +2, my principal used to say, physicist is a seeker after truth, chemist is a seeker after truth, biologist is a seeker after truth. So all of us are seeking after truth. Truth of what? Truth of materials. Okay. Of course, there is other Nobel Prize, peace and literature, that's different, but all sciences are seeking after truth. And as I go on, we will see that why it has been given to chemistry, well, this subject is looking like physics, okay? So, this year's Nobel Prize in Chemistry has been given to Yekimov and Bawendi and Brus, okay? You can see international. Yekimov is Russian, Bawendi is coming from Turkey, I think. No, it's not Turkey, okay. And Brus is, of course, in USA. So, yeah, here. Bawendi is a professor in chemistry from Tunisia, not Turkey, Tunisia. And Professor Brus is Professor Emeritus in Chemistry at Columbia University. He worked mostly in the Bell Labs before, and now he is Emeritus Professor in the Columbia University. And Aleksey Yekimov is the founder and chief scientist of nanocrystal that is in New York, but he is a Russian. Okay. So these are the three people. You can see that. What's happening? Something is happening. Okay, here. So this is the person who started first in Russia, but because of the miscommunication or no communication between Russia and at that time 81, people didn't know what he is doing, so they had to did again, but in a different context. But to start with quantum dot to football is same ratio as football to the whole world. This is, you can say, that is the size ratio. Okay. Now, he is a professor of chemistry at MIT, coming from Tunisia, and Brus is professor of emeritus, Professor Catalogue. He has worked mostly. Are you able to listen at the back side? Okay. So how did it all start? We are, oh, sorry. So it is all starting with the particle electron. You need to know what is electron is, okay? And if you go to, you don't have to do very advanced quantum mechanics. Right in PSC, you see that when a particle is confined into the potential bell, then what happens is energy levels are quantized and depends on the size of the quantum bell, and that is the basic of all this. That has been done a long time. I have been doing a long time back. So when the particle is confined, electron is confined into the material, then it depends on its size, and that's what is being shown here. Here, if the size is larger than smaller, then size is smaller, then the binding is more strong, and the energy levels are having the energy higher. This go to the here. So it started in 1981 when the Russian Yekimov published his discovery that Soviets had, but this research was not available to the Western part. Okay. Then it was independently done by Brus again, but in a different context. Okay, so he started during doctoral degree. He did this glass, and then he heated to 500 degrees centigrade for different 1 hour to 96 hours, and then X-rayed the cool. So then this copper chloride was the material which was embedded into the glass at different sizes. So in some of the glass samples they were only 2 nanometers, and in that they were 30 nanometers. Okay. So then the biggest particle absorbed is light like in bulk, but the smaller particles is not light. So here everybody knows what is periodic table. Periodic table gives you the properties as a function of electrons. More electrons are there, then different atoms are different atoms and different electrons, and that's why. But here it is another dimension is added to periodic table, and that is third dimension is added, and that is size. Okay, at nano level size also matters. Periodic table, different atoms will go from hydrogen, helium, and so on, go up to the last. Then they have different properties, but here the properties change with size. For a given material, in this case it is copper chloride was used, and a given material, the property depends on the size and not on the electrons. Okay. Whereas this was very surprising in the beginning, but then afterwards at 81, this was done by Yekimov, and then afterwards it was done by Bawendi. Brus. So Brus did it because he was doing the cadmium sulfide by a chemical reaction. Okay. So it was if the surface is more, then more chemical, more energy will be. He was wanting to find out how the energy can be converted. So absorption will be more if surface is more. Okay. So by cutting the material to small size, by chopping the material into small size, it creates more surface. And more surface means it will be able to absorb more energy. Okay, surface is, you know, surface is 4 pi r square and volume is 4 by 3 pi r cube. So as the size increases, the surface decreases, and size, if you have smaller size, then total surface increases, and that's why what happened is that this person, Brus, okay, he did in this balance you have larger area in which the chemical reactions would take place. The more is the material chopped up, the greater the surface area exposed. So surface area was the main consideration for him. And then by doing that, he could find out that earlier this Yekimov was done, he has done by in the glass. Copper chloride was embedded into the glass and then heated it. And then smaller particles were changing, and the smaller the particle, more is the energy of the radiation. But here it was doing in the liquid. Okay, so what he did was, but then the main problem was that the one problem was the method Brus had used was fabricate nanoparticles. Here, nanoparticles, they were not under unpredictable quality and unpredictable quantity. So that was the main problem. Although he did. Soon after 81, 82 he did, but then third dimension, this problem demands that how to control the production of the quality and quantity of the nanoparticles or quantum dots. Quantum dot is the smallest nanoparticle. So that was his problem. So then he took a postdoc, and that was Bawendi. Bawendi was the postdoc with he was a postdoc with Brus, and then he started working at MIT. Then he found that the method used that it has to be uniformly injected, and the number of particles are they should have all same size. What was happening in the earlier case in Lewis was all different sizes of the particles are created during their work. Okay, when he was doing that, then Bawendi could devise a method, and that is, what he did was that you inject in the material this cadmium sulfide or cadmium selenide in the solvent, and then you inject right kind of so that the saturation is taking place. As soon as it is saturated, you get more, start making the particles. And then when it cooled down, then it has to be heated again. Then it was again restarted. So here the method was that how to keep on producing the nanoparticles, and that was done by increasing the temperature cadmium selenide, and that's how Bawendi's chemical method was important for that. And that's where the reason comes for the Nobel Prize to chemistry, because although it is a physics process, but this kind of method which could not be done, even this looks like chemistry, okay? And that's why it has been given chemistry, because chemistry method are doing this chemical methods have been used by Bawendi to make the nanoparticles of the similar size and same kind of quality and quantity. Okay, so that's how it happened. And then, so other properties are these luminous properties that 30 years after the discovery of the quantum dots, that was in 82 or something, so 93 was it done. So after 93 it took 30 years to get the recognition, and that quantum dots are finding so many commercial uses. That is, what happened? Sorry. So quantum dots are used in so the applications of the quantum dots or properties of are used in commercial uses, and they are used for change the color of some of the blue light, transforming it into the light activity. So for example, what you can do is, if you have a quantum dot, it will absorb the light and then it will emit, because depending on its size, not because of the material. And that is the most important difference between the. And then they are used, bringing the greatest one is the. But after doing this now, even now, there is a lot of things to be done, and that is exploration is required. And so chronology in brief is that in 80s, Yekimov created size-dependent quantum effects in color glass using the nanoparticles of copper chloride, and then few years later, Brus proved size-dependent quantum effects in particles floating freely in the liquid fluid. And then this person, who is the postdoc with him, he did the main thing, and that was the production of quantum dots, resulting in almost perfect particles. That is, similar size and similar quantity and good quality material. Okay. So applications of quantum dots are enormous, and that is solar cells. Quantum dots can improve the efficiency and lower the cost of energy conversion, then light displays and biochemical imaging. The last talk you have heard about medical thing and lasers. Lasers, quantum dots can be used to create compact and low power lasers. You have heard about autosecond laser in the first talk. And quantum computing. So Nobel Laureates in chemistry have made, this is the, I think the groundbreaking contribution to the discovery and synthesis of quantum dot, opening up the new possibilities. So this is in brief about the research that has been given Nobel Prize. That is producing quantum dot either by heating, that is the first one has done, that is Yekimov, Russian one, and the second one Brus. Okay, he has done by the first one he has done by chemical process. Okay, but this man Bawendi has optimized the method of making quantum dots. Okay, so now I will tell something about what we are doing in this method, in this quantum dots or quantum wire or quantum bell. 0 dimension is quantum dot, 1 dimension is quantum wire, and 2 dimension is quantum bell. Okay, starting from bulk, go to quantum bell, quantum wire, quantum dot. 3 dimension is bulk. So your 2 dimension is the quantum bell and quantum wire. So go to reduced dimension, but the size is about same. That is nanometals, okay, nanometers. Okay. So here, let me tell you something important about this. What is the method how to understand this quantum dot or nanoparticles? There are 2 methods. One is the bottom up, and the other is top down. Bottom up means, bottom up means start with the atom and keep on putting atoms and make the size. Okay, that becomes bottom up. And top down is you have a material, you cut, polish, to go to that. In both the cases, you end up. Everybody knows this atomic energy level. Yeah. So from here to bulk is the semiconductor, or when the atom to semiconductor, these are the energy bands. Okay. But from here to here you can go either by directly here, that is the bottom up, and here it is top down, from the bulk material to quantum dot, or from the atom to quantum dot. Atom to quantum dot is the bottom up, is top down. In each case what happens, the energy band is changing, and that depends on the size. And that's why, because of the size dependent of this, dependent of size gives you how much energy will be given during the here. So main concept is that suppose this is your quantum dot or size of the material here. If your Bohr exciton diameter, what is Bohr exciton diameter? Bohr exciton diameter is the electron and hole moving around each other, that comes a exciton. That is, when you create an electron from the material, then it leaves behind a hole. So the hole becomes like a positive particle. So they revolve around each other. Okay, so that is called Bohr exciton. That diameter, if diameter is less than the material size, then it's okay. But if material size is less than that diameter, then what will happen is that has to be coming to that side, and then what will happen is that electron and hole bound state, that is Bohr exciton. So as soon as it becomes if the size decreases less than the Bohr exciton, then they will have to be the energy band gap. That energy band gap will be bulk into k by d, the size. So as size decreases, energy band gap increases. As the size decreases, energy band gap increases, and that's why what you saw earlier was here. So this D decides how much is the change of the energy band gap, and that decides the frequency or color of the emission or absorption radiation, because that is the main quantity here. It has electron has gone from here, it has left behind, electron has gone to the conduction band, and then it has left behind a hole. Bound state of this electron with the hole, that is the Bohr exciton. If that size is more than the size of the material, then it has to reduce itself, and that's how this energy band gap increases, and that's why that decides the color of the. So this becomes the mathematical formula in which you can see the energy band gap, and hence the color of the radiation or color of the absorption and emission will be depending on the D, that is size of the material. Okay, there is synthesis method. I will not go to details of that. But I will tell you that after that you have to characterize these materials. Characterization is done by various methods like Rutherford backscattering, X-ray diffraction, Raman spectrometry, TEM, and so on, atomic force. These are the characterization methods. You have to see what you have made, and to characterize that, basics of ion-solid interaction comes. That is the interaction between the electron and the material. So that basics is important, and that once you understand that, then it tells you that how to characterize it. And characterization of material is done by, let me go to here. Technique is Rutherford backscattering. So once you have a material, then you have to send your alpha particle or proton to scatter, and that scattering will give you techniques. Rutherford backscattering is, it comes back the information. This can be compared with the method like this. Suppose you want to know something. Here is a material, bulk material, or in quantum dot has, let's say 10 nanometers or something, so 2000, 3000 atoms, and you have to send an external agent to find out what is there inside happening. Okay, so for that, what happens is that you have to you can compare this with a real life situation. Suppose there is a family, and family you want to find out what is happening inside the family. Then you send a person inside the family, interacts and comes out. Depending on how intelligent this is, and that is electron sending it, or alpha particle. So this person goes and comes out with the information, but then it is up to the how why you have to extract that information. That's where the detector also was given Nobel Prize long back. So this is what is happening is that with the whole alpha scattering experiments, they will find out how thin is your nanomaterial, that is quantum bar, quantum dot or quantum bar or quantum bell, and that will be depending on the Rutherford backscattering spectrometry that detects the energy, the amount of backscattered particle, and that gives you the information. Yes, this backscattered particle will give you what information it has collected from the material. Okay. The complementary technique is that is, if you are finding the backscattering is not possible, then you can send a particle, and then it will make the particle inside the broken into many particles, and then the quartz will be merging with the some material, and then okay. So what one does is that these are the materials of interest. For example, in semiconductor physics, gallium arsenide, and you can see what has been produced, the energy band gap. Sorry. Energy band gap versus the various materials, for example, indium arsenide, gallium arsenide. These are both 3-5 semiconductors. And in that, if you put gallium arsenide, indium arsenide, you put some gallium inside here and indium in there, then be somewhere here, and that gives you yes. So gallium arsenide, indium arsenide, these are the. You put some gallium in the indium arsenide or indium in gallium arsenide, then it will be somewhere here, and that. To find out what happens is that how much thin you have made. Yeah, there is a substrate here, substrate of gallium arsenide, and that the deposit layer of indium gallium arsenide, and then or aluminum gallium, depending on which one you. So, if the bulk material is having, let's say, bulk is about, let's say, here by bulk we means about some nanometers, okay. And now that small thin layer has been put few atomic layers, then it has to adjust itself to the substrate. Substrate is your gallium arsenide. So on that, if you put indium gallium arsenide or aluminum gallium arsenide, then what will happen is that it has to adjust itself to the background, to the substrate, and then the lattice parameter will change. And that lattice parameter change will take care of the strength, or that is lattice match the strength. So it will be strength there. That strength will decide what is happening to the material there, and then, for example, here. So here what I am saying, confinement. One-dimensional confinement. Here you have the aluminum gallium arsenide. So this is a small band, energy band gap is. And here you have a larger band gap. So what happens is that if there is a particle in gallium arsenide here, it will be like particle here, gallium arsenide electron, for example, it will be confined because it cannot go here. It is forbidding band gap here. So it will be confined here, and that energy levels in that will decide how much energy has been absorbed or has been emitted. Okay. So that is what is called this quantum bell from here to here. Then if you have into one dimension, then quantum bar and quantum dot. Quantum dot comes here. Bulk material, quantum bell, quantum bar, quantum dot. That is, size is small in only one dimensional here, and then two dimensional here. Then quantum wire and quantum dot is from all the size. Okay. In each case, what is the wavelength of the charge carriers, that is changed because of this. And then what happens is that this process, thermal spike and very Coulomb explosion, that I will not go into details of that. So one can find out that depending on the thickness, okay. For example, here one talks about the 12 nanometers, 36 nanometers or 60 nanometers. For a given thickness and the ratio of this indium gallium arsenide, that will be, as I showed in that curve, that it will be placed somewhere, and that will decide how much strength it is. The indium composition is this, and for a given thickness, change composition, for a given composition, you can change the thickness. In each case, you can find out what will happen and what will be the energy band gap in that case. So, and then what what you get is in this. So the heterostructure of this result in reduced defect density, increased strain upon a radiation irrespective of the thickness and composition of the air. So by this you can make multi-quantum bells, one after the other. That is, each quantum bell is about few nanometers thick. This is the quantum bell is in 2 dimensions. Okay, quantum bar is in 1 dimension, quantum bell is 2 dimensions, and then you can cut it to become quantum dot in that case. So one can see that for each case you can have the multi-quantum bells, and those quantum bells tell you the radiation. If you radiate these materials, then you get two Raman spectroscopy, and then so what happens is, depending on what is the fluence of the ions which you are doing, you can say size of nanocrystal measurement is formed. Okay, crystalline size of the nanomaterial which is formed because of the as a function of fluence of the high energy ions. Because this Nobel Prize has nothing, it has not talked about how can they have made the quantum dots by heating, and other has made by chemical reaction. Okay, but if you can have external radiation like laser, or you can have external radiation like ion beams, swift heavy ion beams. So either giving energy from outside, you can make the whatever you want to do with the crystal size with the radiation fluence. This is ion beams is being used here. Here, the pristine silicon, and then you get very high 400 kV G given, and you get this you do the radiation, ion implantation, and then silica, and then after that you have to do annealing, temperature heating, and then implantation radiation. So what you get is that there is a germanium crystal has been made. Again by radiation. You can see as you increase the fluence, then the size of germanium crystal has increased. Now, what I wanted to explain here is that when you are sending from outside to make these nanocrystal or nano quantum dot, from outside you are then sending, and more is the number of particles you irradiate with, more bigger will be size, because when it is interacting with the bulk material there, bulk by bulk I mean 100 nanometers. Bulk here is 100 nanometers, bulk is not millimeters. Okay. So when it is thick enough, then what will happen is that the more and more bigger nanoparticles will be formed, and here you can see that the size is increasing from 27 nanometers to 31 nanometers. Here. Fluence is after what you have sent from outside this germanium ions, 400 kV germanium has been sent, and then you can see that you can make nanoparticles. In the Nobel Prize they have given by heating, just by heating. Another one is chemical process. Here we are doing externally, either by ion beams or by lasers. Okay, laser also can make this ion beams, it gives energy, and if you choose proper energy, approve proper ion, then you can make these nanoparticles of required size. Here it is 27 nanometers to 31 nanometers increases. So, and then after, how do you do it? By radiation, and then you have to do the post-deposition details. Okay. Here again. Now there is another. This is something which is important to understand. Once you have made the nanoparticles or quantum dot, then if you irradiate after that, then a radiation of these materials after doing the nanocrystals, it will decrease with the influence of the influence, because initially when the influence were used to make the nanoparticles, then it is increasing with the influence. But if you are, once they are made by any other method, then if you irradiate those particles, then it decreases size. Earlier it was increasing the influence, number of ions which are used for variation of average nanocrystal size with the radiation influence. What the difference between these two processes is that initially you are making the nanoparticles by depositing the particles on starting and integrating. But once they have been made, then you send the ion beams, then it will step up from the size, and that's why size is decreasing. This decrease of size is because as you increase the influence, number of ions per centimeter square on the nanocrystals, then it is decreasing because whatever from the nanocrystal or quantum dot size, then nanocrystal size, it takes away the atoms. More and more is the influence, it decreases the size of that, okay. That's why it is just the reverse. Initially it was when you are making, then you are depositing, and you will deposit more when the nanoparticle is being made. But once it has been made, then if you radiate, then it will decrease. So German nanocrystal increase in the influence, average size of German nanocrystal decreases in influence and radiation influence. Raman peak shift gives that information, and then the nanocrystal partially amplifies as a result of ion radiation. Okay, then there is another thing which is there. What is the material in which you are hosting these nanocrystals? One is the mostly it is silicon. Silicon has the indirect band gap. Okay, but if you have hafnium oxide, characterization embedded in hafnium oxide instead of silica or crystalline material. So this is the difference between that. You can see silicon oxide is here, dielectric constant is, and hafnium oxide. One can ask why is silicon oxide and versus hafnium oxide? Because dielectric constant is more here and the energy band gap is less. Okay. So when you are using this, then dielectric constant, that gives you the capacitance. That is the energy storage properties here. So if area of the material is there and D is less, then C is more. But once you have saturated on this, then only thing you can change is the dielectric constant. And dielectric constant is increases, then you can have more energy storage. That is the purpose of this. By silica versus hafnium oxide. Silica is something here, there, you have the silica is here, so the dielectric constant is much less, but hafnium oxide dielectric constant is much more. That's why when you use the hafnium oxide, so that you can have C increase, that is the energy storage capacity increases for same area, same thickness and same area size. Because you want to make so many of the devices on the same chip. So you cannot make too much of area, and you have to have, there is a limit of thickness, you cannot go below certain thickness. So the C has to increase only by dielectric constant. That's why hafnium oxide is chosen instead of silica. One can say why not this? But here the energy band gap is very small. So this is the optimum thing. Hafnium oxide is used for this material, high K materials, quantum tunneling, and get the current. That is the purpose of using hafnium oxide instead of silicon oxide. Here something has been said here again. So you can see that on a substrate you can have the hafnium oxide and then make these. Some silicon substrate you can embed the germanium nanoparticles into the hafnium oxide instead of silicon oxide. Because this has a higher dielectric constant, so it will have more C, that is more energy storage, and because of that ion beam radiation has been used for synthesis of nanocrystals in the ice deposits. So that is the purpose of using hafnium oxide instead of silicon oxide, and 10 to 15 nanometers of germanium. So silicon, the SHI will shift heavy ion radiation, this is the information of germanium nanocrystals in hafnium oxide. Again, the same process is there, that when you radiate by the shift heavy ion radiation means 100 MeV or 150 MeV germanium, silver or gold. Okay, so those radiation give the energy, deposit the energy, and they make the germanium nanocrystals, and the thickness increases as the dose increases, and then you can see that nanocrystal size increases with the annealing temperature. And that changes the changes on the structural and electrical properties of thin deposits in gallium arsenide. I will not go to the details of this, I will show you the results. And finally, we can talk about laser annealing. That is, annealing means you can have annealing by temperature annealing or laser annealing. Laser also deposits energy, but there is a difference between thermal annealing and laser annealing. Laser annealing can be also, so that is true with the Swift-Avian radiation also. You can have, it can be spatial, that is, you can do it at wherever you want. Thermally, entire thing is heated, okay, but laser annealing you can have very small area where you can anneal. So you can make one kind of device at one place, another kind of device another place. Okay, that's why this laser annealing or the Swift-Avian annealing used. And the same thing is done here. Yes. The alternate techniques like laser annealing can improve the hafnium oxide based MOS devices, especially by minimizing defects in the hafnium oxide cells. Because then you use the ion beam irradiation, then you get some defects. But laser annealing, and this is not the attosecond, this is only nanosecond laser, picosecond laser. That laser does the wonders to find out to do the laser annealing and make the devices. Yeah. The gold nanoparticles have been made and used well. The result of this study is the use of non-thermal laser annealing technique in synthesizing an array of high-density gold nanoparticles on the surface of hafnium oxide, then without altering the phase of HFO2. Because if you use there is a difference between laser and ion beam. Ion beam will change the, it can change the, because of it deposits energy, and it will be spatial, of course. Both laser and ion beam annealing is both spatial, but ion beam can create lot of damage. So laser is the one which is laser annealing, and this is not the nanosecond laser or picosecond laser is enough. Nanosecond mostly is used. That gives you the enough surface. Laser ablation. Here. That is size of the nanoparticles. Here they are made here, and the size distribution of silicon nanoparticles in the TM images confirm the formation of silicon nanoparticles by laser ablation of silicon vapor in acetone, and this is observed from the image that the radiation creates a hazy outline around the nanoparticles which leads to the growth of the relatively small nanoparticles observed in the density of nanoparticles increases with the increase in radiation influence that we already have seen. Oh. Sorry, I am pressing the wrong button many times. Okay. The smaller size nanoparticles increase in laser fluence. The smaller size nanoparticles of size 9 nanometers are forming around the big nanoparticles. This is to an induced breaking of the silicon nanoparticles. So observe that average the size of the germanium nanocrystals decreases with the increase in ion fluence from a starting from an images. So again, the TM images of the nanoparticles that has been made into various. The main underlying study and underlying idea is that instead of using only heating or either laser and ion beam, these are the two external probes. The external probes can be used to have a spatial distribution of the nanoparticles that you are forming. And their size and density can be changed by fluence. Fluence changes the fluence means this nanopart shift area and fluence or laser intensity energy. Okay, so in that case you have very good control. Instead of initial research was done in heating by the Yekimov was heating. Heating means you have to heat in something, but here you can have a spatial distribution. That is the main thing. New nanoparticles because these are the TM images. Okay, so the redshift indicates increase in nanoparticle size. When the nanoparticle size increases, the nanoparticle size increase means you have the redshift, means the frequencies towards smaller nanoparticle will have a blue shift and bigger nanoparticle will have a red shift. That's what is well known fact by now. And then these are again something repeating. Well, there is one important thing here. What I am trying to say is that one can have the silicon nanowires. Okay, deposited on a substrate, you can have nanowires. Okay, that is nano-sized wires. Instead of having nanoparticles, you can have nanowires deposited on that, and that can be done by eta 100 silicon polished side, and then step to the then right, and then what you get is silicon plus 4 Ag hafnium fluoride. Yeah, and then these are the forms. One can ask why do we need them? Okay, and that is the purpose of that is that you get density of these silver nanoparticles and silicon nanowires increases with increase in dipping time. First you make the silicon nanowires, and on that you deposit the silver nanoparticles. What one is doing is that many nanowires are formed, and on that you deposit silicon nanoparticles because they are on the top of the surface. Increase surface is more. Main purpose is to have more surface. So what happens is that in that case, yeah, so there is a silicon wafer, and then on that silicon nanowires have been made. On that you deposit silver nanoparticles, and then scattered from a signal. Scattering takes place from the silver nanoparticles. And then more is the surface, more are the wires, and more is the surface, and that because of that you get more signal. So that was that is Telangana. That when we published that was immediately it was. I got a call from Telangana. So we said that how this can be this thing can be used. This kind of work can be used for example the finding the security. This kind of thing can to find out what is there in the silver nanoparticles are there surface. You can use it for security, and then okay, thank you. So the same two sentences, the difference between normal way of making nanoparticles or quantum dots and by using the external probe, external high ion beams or laser is, it is spatial and you can control it. Whereas in that work, the Nobel Prize has been given, but you cannot control it. And Bawendi did control something by injecting this thing. That slide I showed that you can inject now you can make the saturation by injecting the thing. And that's how he was included. But first of all, this Yekimov and Brus. Yekimov by the heating, and this by chemical process, chemical reaching. In both cases, you do not have a spatial control. But ion beams and lasers can have a spatial control. Means where you want to make, you can make it, and on a given chip you can make so many. And this is being done by doing the spatial control and having the same substrate. When so many devices by having different kind of nanoparticles. That is the main difference between this, and this work is being now continued here, and we have collaborators. Okay, thank you.
Thank you, sir. We request you to be on stage for some more time. It was really an thought-provoking talk, and I'm sure that